Hello, everyone. Today, we're diving into a really critical topic for anyone in pharmaceutical quality control, nitrosamine impurities. You know, these tiny compounds have been a huge challenge, but a brand new, internationally agreed upon approach is here, and it's set to change the game. So let's break down exactly what this new method is and how it's going to work for you.
You know, it sounds a little dramatic, almost like a movie plot, right? But for the last few years, this is a question the entire pharmaceutical industry has been grappling with. And that hidden danger? It's a class of impurities called N-nitrosamines. Now, the risk is incredibly low, but as you know, patient safety is everything, and that's exactly why this is such an important conversation to have.
So what are we actually talking about here? Well, N-nitrosamines are these chemical compounds that can sometimes form during the synthesis or even the storage of a drug. The big deal, the reason we're all so focused on this, is that many of them are potent mutagens. That means they can damage DNA, and because of that, they're classified as probable human carcinogens. It makes controlling them an absolute non-negotiable priority.
Now, this isn't a brand new issue, but it really exploded into the spotlight back in 2018. You probably remember the recalls of those blood pressure medications, the sartans. That single event really kicked off a massive, coordinated effort around the globe. Regulators from the US, Europe, Canada, Japan, you name it, they all came together and formed the Nitrosamines International Technical Working Group, or NITWG. The goal was simple: get on the same page. And it was that incredible collaboration that led directly to the new method we're digging into today, the CPCA, which was just formally published in 2024.
Okay, so if regulators were already on the case, you might be wondering, why did we need a whole new system? And that's a great question. The thing is, the old methods were starting to hit some serious walls, especially as these new and much more complex nitrosamines started popping up.
The main problem was the emergence of something called NDSRIs. That's nitrosamine drug substance-related impurities. These are nitrosamines that are structurally related to the drug itself, and for most of them, there was just no cancer data available. Zero. The usual approach, what's called read-across, is where you try to find a similar, well-studied molecule, a surrogate, to estimate the risk. But for these new, complex impurities, finding a good surrogate was next to impossible. This created a huge bottleneck, and worse, it led to inconsistencies between different health authorities. It became really clear that a new, more predictive tool was desperately needed. And that brings us right to the solution, the carcinogenic potency categorization approach, or CPCA. This is the breakthrough that the International Working Group developed to bring some much-needed clarity and consistency to the whole business of nitrosamine risk assessment.
So, what is it at its heart? The CPCA is an incredibly powerful predictive model. And this is the crucial part. It lets scientists predict a new impurity's cancer-causing potential just by looking at its chemical structure. You don't need to run new, lengthy, and expensive animal studies. And because it was built by this consortium of global regulators, it gives everyone, everywhere, a single, harmonized framework to work from.
Okay, so let's get into the nitty-gritty. How in the world can you predict something so complex just from a drawing of a molecule? Well, it all boils down to understanding the one specific chemical reaction that makes a nitrosamine dangerous to begin with.
So, this right here, this is the critical first step. For a nitrosamine to become a carcinogen, it has to be switched on, or metabolically activated by enzymes in the body. This process is called alpha hydroxylation, and you can think of it as the key that unlocks the door to potential DNA damage. The entire CPCA model is built around one thing: predicting how easily a specific nitrosamine molecule can undergo this exact reaction.
The model does this by looking for specific structural features on the molecule and then sorting them into two categories: activating or deactivating. It's almost like a scorecard for risk. The activating features are parts of the molecule that make that alpha hydroxylation reaction easier to happen, which, in turn, increases the cancer risk. The deactivating features, on the other hand, do the opposite. They get in the way of the reaction, or they help the body clear the molecule out safely, which lowers the risk. And you can see from this table how tangible this all becomes. Every one of these features gets a number. A really strong deactivating feature, like a carboxylic acid group, gets a big positive score, say a +3. A feature that bumps up the potency a bit, like a methyl group on the beta carbon, gets a negative score, like -1. You are literally doing a chemical risk calculation, piece by piece.
And the calculation itself, it's pretty straightforward. You start with a base score that's related to the alpha hydrogens. Those are the atoms that are right at the center of that key reaction. Then you just add up all the positive scores from the deactivating features and subtract all the negative scores from the activating features. You add them all together, and that gives you a single number, the final potency score.
And this chart here shows you where the magic happens. That potency score isn't just some abstract number. It directly maps the nitrosamine into one of 5 potency categories. And each category, from 1, the most potent, to 5, the least potent, has a very specific acceptable intake, or AI limit. And that AI limit tells you the maximum amount that's considered safe for daily exposure.
Now, this whole system isn't just pulled out of thin air. It is built on a solid foundation of established regulatory science. For example, that AI limit for the least potent categories, 1,500 nanograms per day, it's based on the threshold of toxicological concern, or TTC. This is a widely accepted principle from the ICH-M7 guideline for limiting cancer risk. So this ensures the CPCA is both innovative and totally grounded in health protective principles we already trust.
All right, theory is great, but let's make this real. Let's walk through how this actually works in practice with a couple of real-world examples you might actually see in the lab. First up, we've got N-nitrosopropanol. This is the NDSRI that could potentially form from propranolol, which is a very common beta blocker. So let's see how the CPCA sizes up its risk.
Okay, let's do the math. First, we assign the alpha hydrogen score. In this case, that's a +3. Then we look for other features. We spot a hydroxyl group on the beta carbon. That's a deactivating feature, so it gets +2 points. We also see an arrow group on the alpha carbon. That's an activator, so it gets a -1. So you add it all up. 3 + 2 - 1 gives us a final score of 4.
A score of 4 puts N-nitrosopropanol squarely into potency category 4. And what does that mean? It corresponds to an acceptable intake limit of 1,500 nanograms per day. So the model is telling us it predicts a low carcinogenic potency. It's as simple as that.
Okay, now for something a little more complex. This is an NDSRI from valsartan, one of the very drugs from that original 2018 recall. As you can see, its structure is quite a bit more complicated than our first example.
So let's run the numbers again. We start with the alpha hydrogen score, which is +3. This molecule has 2 activating features, a beta-methyl group and a benzylic arrow group, and they each score a -1. But, and this is a big but, it also has a very powerful deactivating feature, that carboxylic acid group, which scores a +3. So the math is 3 + 3 - 1 - 1, which once again gives us a final score of 4.
And there you have it. A score of 4 means potency category 4, with an AI of 1,500 nanograms per day. I think this is a perfect example of the CPCA's power. We have 2 completely different molecules, but the system just analyzes their features and arrives at the exact same science-based conclusion about their potency. It's brilliant.
Okay, so let's wrap this up. What's the big picture here? What are the real implications of the CPCA for those of us working in quality control every single day?
Bottom line, the CPCA gives us a clear, predictable, and scientifically sound framework. When we find a new nitrosamine impurity, we can now figure out an acceptable intake limit without having to wait for new animal studies. This means more consistency across different regulatory agencies, which is huge. And most importantly, it protects patient safety with a really conservative approach. Best of all, it's designed to be a living model, which means it's ready to be updated as the science gets even better.
This really is a massive step forward in the world of predictive toxicology. It just makes you wonder, as these kinds of computational models get more and more powerful, are we heading towards a future where we can accurately predict the risk of any potential impurity before a single molecule is even made in the lab? It's a fascinating thought to end on. Thanks so much for joining this Explainer.